This video will cover section 3.6. We'll talk about area between curves, the volume of revolution, and average value, and we'll see examples of each of those topics. Let's start with the area between curves. We've already used integrals to find the area between the graph of a function and the horizontal axis. Integrals can also be used to find the area between two graphs. If f of x is greater than or equal to g of x for all x in an interval, then we can approximate the area between f and g by partitioning the interval from a to b and forming a Riemann sum as shown in the picture. So we'll break it up into rectangles just like we did in previous sections when developing the indefinite and definite integral. The height of each rectangle is top minus bottom, so that would be the top function, which is f of x, minus the bottom function, which would be g of x. And so at a particular point c sub I, that would be f of c sub I minus g of c sub I, so that the area of the ith rectangle, which the area of any rectangle is height times base, would be f of c sub I minus g of c sub I times delta x, which is the width of every rectangle, and we try to keep delta x the same over each rectangle. If we add up these rectangles, it gives us an approximation of the total, which is the Riemann sum from I equals 1 to n of f of c sub I minus g of c sub I, and that times delta x. The limit of this Riemann sum as the number of rectangles gets larger and their widths get smaller is the definite integral from a to b of f of x minus g of x dx. So this is the area between two curves, which we'll see formally written on the next slide. So the area between two curves f of x and g of x, where f of x is greater than or equal to g of x between x equals a and x equals b, is the integral from a to b of f of x minus g of x dx. And so the integrand will always be the top function minus the bottom function, and the key will be to always graph the region first to ensure the integrand is correct. So we'll always draw a representative rectangle when we're setting up our integral to make sure that we have the top function minus the bottom function so that the height comes out positive and we don't end up with a negative area. Let's take a look at an example. We want to find the area between the graphs of f and g for x in the given interval, and be sure to draw the graph. So in this, we'll have that f of x is x squared plus 3, g of x is 1 plus x, and we're on the interval from 0 to 3. So let's take a moment to graph this region. Okay, we have our region where f of x is x squared plus 3, g of x is 1 plus x, and we're looking between x equals 0 and x equals 3, so I've drawn those green vertical lines. If we draw our representative rectangle to make sure that the top of the rectangle touches the top of the function and the bottom of the rectangle touches the bottom of the function, we can see that we'll be setting up our integrand f of x minus g of x. Now, it's not always going to be f of x minus g of x. It really just depends on which function is the top function over the entire interval. So we could have had an example where g of x was larger than f of x, and in that case, we would do g of x minus f of x. So let's set up our integrand. Remember, when we're finding the area of a region on the interval from a to b, it'll be the top function minus the bottom function. In this case, f of x is our top function, not always the case. And then we're integrating with respect to x, and that's determined by how you're taking slices. Since we're making vertical rectangles, they're taking slices out of x. So we're integrating with respect to x. So just a reminder, this is top minus bottom. So the area will be the integral from 0 to 3 of x squared plus 3 minus 1 plus x dx. We'll simplify the integrand, which becomes x squared minus x plus 2, and then we will take the integral using the power rule for antiderivatives. And so we have 1/3 x cubed minus 1/2 x squared plus 2x plus c evaluated from 0 to 3. By the fundamental theorem of calculus part 1, we will evaluate the antiderivative at 3 and then subtract the antiderivative evaluated at 0. And so the area between f of x and g of x on the interval from 0 to 3 is 21/2. Let's look at the volume of revolution. This will start with a bounded area, and then we'll take that bounded area and rotate it about the x-axis. Just as we can partition an interval and imagine approximating an area with rectangles to find a formula for the area between curves, We can partition an interval and imagine approximating a volume with simple shapes to find a formula for the volume of the solid. We start with an area, the region below a function, on the interval from a to b. We're going to take that region and rotate it around the x-axis, creating a solid shape shown. So if we assume that we start with a basic region bounded by some curve f of x and the x-axis between the values a and b, and then we rotate this about the axis, we end up with this cylindrical shape here. To find the volume of the solid, we can start by partitioning the interval, and this should say from a to b, not just restricted to 0 to 1, and approximating the area with rectangles. As before, the width of each rectangle will still be delta x, and the height will be the function value at a particular value on the interval. So we'll call it f of c sub I, where c sub I is just somewhere in this interval. If we took just one of these rectangles and rotated it about the horizontal axis, it would form a cylindrical shape. It's a three-dimensional cylindrical shape where the radius of that cylinder would be the height of the function, f of c sub I, and then the volume would be pi r squared h. That's a volume for a cylinder, and h is going to be that dx, the width of the rectangle. That's your h, or your dx, delta x. And so the height is your radius. The volume of the whole solid could be approximated by rotating each of the rectangles about the x-axis. Adding up the volume of each of the little cylindrical discs gives an approximation of the total volume as a Riemann sum, which would be the sum from I equals 1 to n of pi times f of c I squared delta x, where this value is pi r squared because the radius would be the function value. So formally, if we take the limit as n approaches infinity of the Riemann sum, we end up with the indefinite integral for volume on the interval from a to b as the integral from a to b of pi times f of x squared dx. Let's look at an example, making sure to first graph the region. We want to find the volume of the solid that's obtained by rotating the specified region about the x-axis, and the region we're looking at is underneath f of x equals 4 minus x squared, bounded by the x-axis, and then only from 0 to 2. Let's start by drawing the picture. So we are rotating the region under f of x equals 4 minus x squared. We're looking at this region from 0 to 2. It's going about the x-axis. And so what I'll do is draw a representative rectangle. That will help me identify what the height is, which is always going to be my delta x once I create my cylinder. And then the radius is always going to be the height of the function from the x-axis out to the curve. So that's going to be my f of x. So the formula for volume is the integral from a to b, pi r squared h, or pi times f of x squared dx, the delta x. So plugging in these values, we have the integral from 0 to 2, because my slices will go starting from 0, and I'll make my rectangles all the way until the end of my region. And then pi times 4 minus x squared dx. I'll then want to pull out my constant pi using the rules of antidifferentiation, and I will multiply out 4 minus x squared so I can use the power rule on each of those terms. So I'm looking at the integral from 0 to 2 of 16 minus 8x squared plus x to the 4th dx. And so I'll be looking at pi times 16x minus 8/3 x cubed plus 1/5 x to the 5th plus c evaluated from 0 to 2, and I'll use the fundamental theorem of calculus to evaluate. And so the volume of the region under 4 minus x squared from 0 to 2 is 256 pi over 15 units cubed. And it would be units cubed because it would be a positive volume, since the region that's bounded is positive because the whole region is above the x-axis. The last topic we'll discuss will be average value. The average value of a function on the interval from a to b is 1 over b minus a times the integral from a to b f of x dx. In general, the average value of a function will have the same units as the integrand, and remember the integrand is usually a rate of change. So we want to find the average value of f of x equals x squared on the interval from 0 to 2. The average value formula is 1 over b minus a times the integral from a to b of f of x dx. So our a is 0 and our b is 2. And the average value of this function on that interval will be 1 over 2 minus 0 times the integral from 0 to 2 of x squared dx, or 1/2 1/3 x cubed plus c. If I use the power rule for integrals to find the antiderivative, that will be evaluated from 0 to 2 because it's a definite integral. 1/2 times 1/3 is 1/6 times 2 cubed minus 0 cubed. The plus c's cancel, and we're looking at 8 over 6, or 4/3. And that would have the same units as f of x if we were to know them. The last video for this chapter will cover applications to business using integrals.